All right, so again, we're going to be talking about electrons in atoms. All right, and really what we're going to be doing is sort of refining our idea of what is our atomic model. Right? What do we think an atom looks like? Up until now, we've been pretty vague on that. We've made some sort of statements about our atomic model, specifically the subatomic particles. We have our protons and our neutrons, and the other ones are the electrons. And we know that these protons and these neutrons, they live where? Yeah, they live in the nucleus. And the electrons live outside. Okay, cool. That's kind of what we've said. We didn't say much more than that at this point about our atomic model. And so that's kind of what we're going to be refining. Like, we're really actually not going to talk much more about our nucleus. It turns out that they're not the most interesting structure if you have protons and neutrons. They just kind of sit all packed together. All right, so this would be a great sort of picture of a nucleus here. It's quite tiny, very, very tiny, and it lives at the very center of every atom, right? What we're really interested in, and the title of the chapter, is the electrons in our atoms. What is the structure of those electrons that make up our atom, okay? You know, the other reason that we really care about this is because electrons are the things that are involved in bonding. The protons are there to serve as that positive charge in the middle, but a lot of the interesting stuff happens with the electrons. So we're going to spend a lot of time defining our picture of what electrons look like in atoms, okay? So first of all, just to kind of go through the history of the atomic models, it starts out with what they call the solid sphere model, where basically the whole idea is that atoms are just like marbles. Right? That was the first picture of what atoms were, where they were just teeny tiny marbles, really, really small. But basically a lot of the physics that was applied to things like marbles, to things like baseballs. You can imagine a famous physics problem of throwing a baseball across the room and tracking it using math, right? They were able to do some of that same stuff with atoms, so they're like, okay, it must be the same idea, just a little marble. And then they got the technology to look at these charged particles here, so they knew that there were both electrons. I think that's what they discovered first, is that there are little electrons, and so they figured out, assumed that it was just sitting in this sea of positive charge, what is called the plum pudding model. I'm not sure why they couldn't do better than that, but go. All right. And then what we kind of started out with was this nuclear model here. All right. The idea that the positive charge is in the very center and the electrons are on the outside, but we really didn't say much more than that. Okay. What we did sort of learn about that would have been more in line with the Bohr model is this idea of valence electrons, right? So that's kind of what the Bohr model did that everybody liked, was it essentially said, okay, these electrons aren't just willy-nilly flying around, but there's some sort of order to them, some sort of energy to them. And he kind of pictured it as if it were planets orbiting the sun. So in the center is your nucleus, and then you have electrons kind of orbiting around. And depending on how far they are, that would be the energy of those electrons. And so those outermost ones, the ones that are the easiest to remove, are literally in his model outermost. They're the physically outermost electrons. Okay? That didn't last for very long. So basically kind of around this time, you see this accelerated timeline here. Okay? And that's because at the turn of the century, what happened is this massive destabilization in Europe and the world wars that sort of followed. And for the first time, governments were throwing money at science like they hadn't really done before. So all of a sudden, physics and chemistry was really being pushed and being prioritized in a way that it kind of wasn't. So things really sort of took off. There were very young people. Schrodinger's like 23 at this point when he does this theory. Einstein's like 23. It was pretty early because all of a sudden that stuff was really encouraged. And what they basically did is they developed this model called quantum mechanics, which said that sort of classical mechanics, that Newtonian physics, doesn't actually work for these teeny tiny particles. We need to build a new math. And that's what Einstein and Schrodinger are known for. They built this new math, and that it correctly explains the world around us. It's even more complicated than calculus. So most of you right now are on your journey to learn calculus. Don't worry, there's even worse math out there after that. There's a whole nother algebra that you could learn. It's actually pretty cool, but there are some differences to that sort of Cartesian XYZ waves explaining the world that calculus tries to do. And so, if we look at our hydrogen atom according to quantum mechanics, we have this brand new ridiculous mathematical equation here. Like I said, a completely different algebra than what you've learned previously. All right, so let's get going. We're going to learn this math real quick. No, I'm kidding, that's ridiculous. But this is kind of what that equation looks like. And this is what a hydrogen atom is in the world of quantum mechanics, is the solution to this math problem here, right? So when we talk about our modern model of an atom, it is really a physics problem. It is a math problem. And it's what we understand is the solution to that math problem. And that's because quantum mechanics has worked really freaking well thus far, okay? Importantly, what you're solving for, and it appears on both sides, so we see our both sort of weirdness about this world of quantum mechanical math here. Anyways, this thing is what's called the wave function. All right, and it is what you're solving for that's telling you the probability of finding an electron in a particular place. I guess just in space would be the best way to say that. Okay? And the name of this function I sort of bring up because it hints at what the quantum mechanics world did that classical mechanics didn't, and that's what was to treat things as if they were waves, all right? So electrons aren't little marbles, they aren't little hard spheres. We're gonna instead treat them as waves. Honestly, it's a little bit more complicated. They're probability waves, but whatever. We're gonna treat them as waves, and that's what that math does that's so differently, that kind of helps explain the world around us in a way that classical mechanics couldn't. And so this is what we're solving for, is our probability of finding an electron in space. And I know that this was super obvious to you all as soon as I put it up on the screen, but the solution to that wave function is this big ugly thing right here, right? Duh, everybody knew that, okay? Now, importantly, what we're gonna be doing is no amount of math, but we're still gonna be understanding the results of this equation right here. We're gonna sort of be simplifying things into these pictures, these mental pictures of orbitals that look like spheres or maybe little peanuts. They have these different shapes. But importantly, when it all seems really weird and you're like, where the hell did this come from? It's not me making it up. It's nobody making it up. It's the math. We gotta blame the math when things seem a little funky here, all right? Cool. So, wonderful. What we're gonna do is we're gonna start talking about electrons here, and I'm gonna introduce these different orbitals to you. The first one is, and actually let's talk about what we mean by orbital. So an orbital is an electron cage. And that is obviously a very simplistic way of thinking about it, but it's a great way to think about it. Our electrons in our atoms are kind of trapped in these orbitals. They're trapped in these little cages here, okay? As I said, it's kind of a probability function, so they kind of imagine that the electron is zipping around in this atom, but not in a super random way. It spends most of its time close to that center there. And what's at the very center of the atom again? The nucleus, okay? And again, we're gonna define this sort of sphere here of where most of that electron density is kept. Honestly, think about it as an electron cage, all right? Cool, so the first orbital that we're gonna look at specifically is what's called an s orbital. And the S here stands for spherical, because these are spherically shaped orbitals. Right, again, in the very center, okay, so just to be clear, if this is my s orbital, which it is, this dot is the probability of finding an electron. right? It's the solution to that big ugly math problem that we plotted here, and that big ugly math problem tells us the probability of finding an electron. So each one of these dots is the probability of finding that electron. We can see we're most likely to find it close to the nucleus, and then it kind of spreads out from there in this spherical shape, so in 3 dimensions here. All right? This is like the correct way of looking at this sort of math problem here. What we do instead, because we're lazy, is we sort of imagine it instead as these hard sort of spheres here, right? But again, this is our electron cage. Our electron is trapped inside this spherical orbital here. In terms of orbitals, the S1 makes the most sense to me. I mean, it's a sphere around that center nucleus where the electron is. Cool, that seems to make sense, all right? The other ones aren't necessarily going to be as intuitive. So the next one is what's called a p orbital. All right, and that is because these orbitals are peanut shaped. That is the technical term. Okay, so we had our s orbital that was a sphere. This is now a p orbital, which is this sort of like hourglass kind of shape here, but it's the same concept. We have our electrons that are trapped in these orbitals here. They're able to bounce around within this peanut shape, but it's trapped in that peanut-shaped orbital. All right. There are actually 3 p orbitals. Okay, the difference is they all have that same peanut shape. They're just oriented differently in space. So if we look here, this one is pointed up and down, all right, hugging that z-axis. If we flipped it over on its side, that would be our next p orbital. And if we turned it another 180 degrees, that would be this one here, right? So they're that same peanut shape, our 3 p orbitals, but they're just oriented differently in space. Okay? Importantly, you don't have to know px, py, pz, anything like that. What you need to know is that there are 3 p orbitals and that they're peanut shaped. Okay? Cool. So then we have our d orbitals here. Everything's going to just kind of get more and more complicated. These d orbitals are because they are daisy shaped. And yes, I am making up these words here, but they are very helpful in keeping in mind the shape of our orbitals. All right? So if we go to our d orbital here, we can see that it's kind of like 2 p orbitals smashed on top of one another. Right? We have this daisy-shaped orbital. Okay? And just like before, our electrons are trapped in these orbitals here, these little cages. So they're kind of zipping around freely in these spaces here, right? But they're trapped in that daisy shape around, what's in the middle? The nucleus, around that center nucleus. Okay? There are not 3, but 5 different d orbitals. Okay? If we look again, they're that same daisy shape, just sort of tilted around, oriented differently in space. If I took our first one and flipped it on its side, then we would have it, or rotated it, then we'd add that one, flip it around, that one, okay? And then there's one oddball. This thing right here is much more like a p orbital, but then it has a donut around the middle. So we got one weird donut one here. And so for our d orbitals, we're going to remember daisies and donuts. Those are the shapes of our d orbitals. Now, how did I know that there was one oddball that had a donut around it? How did anybody know? Again, what are we going to blame it on? The math. It was that big ugly math equation. It turns out that if you solve for one of those orbitals, one of them is a peanut with a ring around it. Not something people just came up with off the top of their head, right? It's the crazy world of quantum mechanics that math problem showed us. There's one more, the f orbitals. I don't expect you to be able to recognize these ones other than they're just way more chaotic. Okay, there's just more and more little lobes to each of these orbitals here. What's important is what is the total number of f orbitals that we have here? 7. Okay, so there are 7 different ones. Okay, so again, our whole goal that we've been doing here is to refine our model of the atom here. We said that electrons live outside the nucleus, right? Well, now we can go even further. We're focusing on our electrons here. All right, our electrons, where do they live? They live in orbitals. All right, we got these different shaped orbitals here that we've discussed. The s orbital. We said S was for sphere. Okay, and there was only one s orbital. There was only one of those spheres. We got to the p, to our peanut shaped. And how many different peanut shaped orbitals did we have? 3, right? There were 3 different ones. They were all the same shape, but they were oriented differently in space. Okay, so we're just going to make a note, 3 orbitals. All right, and then the D. We said it was daisies and donuts. How many orbitals? 5. All right, and then the F, I said I'm not going to expect you to recognize, but we'll say they look like flowers, kind of. All right, and importantly, how many were there? 7. All right, so notice the pattern 1, 3, 5, 7. All right, increasing odd numbers here. You want to keep this sort of order S, P, D, F in mind. It's going to come in handy in a few different ways that we're going to discuss here. All right, it's kind of just this natural ordering of these different orbitals here. And again, where did the sphere and the peanut and the daisy and the donut come from? They come from that wave function. These are solutions to that quantum mechanical problem. Okay, cool. So now I'm going to talk about what are called electron configurations. All right, and what our electron configurations are a summary of all the electrons in an atom. We're going to make a list of all the different electrons that we have in a particular atom. Cool. So what's going to happen here is I'm going to show you some of these electron configurations. We're going to pick them apart, make sure we understand what we're looking at, and then we'll learn how to build them ourselves, all right? So you're not going to know how I got these at first, or maybe you remember. You're just going to trust me at first, and then we'll learn how to build them, all right? So our first one, our electron configuration for hydrogen is 1s1. All right. One of these things look familiar because we've just spent forever discussing it. What's that? In our little configuration here. Which one of these do we sort of understand? The S. Because the S corresponds to the shape. So this tells me that my electron in this hydrogen atom is trapped in one of those spherical shaped orbitals. Okay? So more importantly, we have our shape information here. The superscript up at the top tells you the number of electrons in that particular orbital. So hydrogen, which is just 1 proton. So if I have a neutral hydrogen atom, it's going to have 1 electron. That 1 electron lives in a spherically shaped orbital. All right, and then this number out front here is what's called the principal quantum number. And I'm going to kind of gloss over this one for right now. All right, we'll come back to our principal quantum number. Okay, so now our next element is helium. Based on how many protons helium has, if I have a neutral helium atom, how many electrons does it have? Just 2, right? It's element 2 on the periodic table. So if I have a neutral helium atom, it's got 2 electrons. So again, I'm going for where do those electrons live, my electron configuration, which for helium is 1s2. Okay, so both of those electrons in that helium atom live in a spherically shaped orbital. All right, the next element, element 3 on our periodic table, is lithium. So it's going to have 3 electrons. Its electron configuration is 1s2, 2s1. All right, so importantly, these are both spherically shaped orbitals. All right, but they differ in the principal quantum number here. One is the 1s orbital, the other is the 2s orbital. All right, so what the heck do I mean by my principal quantum number? Let's take a look at this 1s and this 2s orbital. Okay. All right, so what we have here is actually 3 different s orbitals, our 1s, our 2s, and our 3s orbitals. Okay, all of them are spherically shaped, but they differ in that principal quantum number. All right, so first of all, first thing to note, most important thing to note, is their size, right? As I increase in my principal quantum number, the physical size of that orbital also increases. It's just a bigger orbital, okay? So if we go back to our electron configuration for lithium, 1s2, 2s1, it means there are 2 electrons living in a little sphere, and there is 1 electron living in a larger sphere. All right, so the size of our orbital increases as we increase that principal quantum number. Now, of course, it can't be that easy. There are these other things that you'll see as you increase, you introduce what are called nodes. All right, so a node in our orbital is an area of 0 probability in that wave function. Which again, remember, tells us where our electron is. What up?
The node is the space?
Is the space, yep. Okay, so as we increase in our principal quantum numbers, we introduce these nodes into our orbitals, and these are areas of 0 probability in our function that tells us where our atom is. All right, so if we look at our orbital here, again, yes, it is that empty space between these 2 different spheres. They colored them in different colors here to highlight the presence of this node. And then we got another one here. Okay. So this is another one of these bizarre features of quantum mechanics. This is saying that our electron is going to be zipping around in this space here. It's going to be zipping around in this space here and this space here, but it's never going to be in that node space in the middle. Okay? So this is another one of these fantastical world of quantum mechanics kind of example. If I took this pencil and I wanted to huck it at that backboard, all right, the only way I could do that is if at some point it passed through the middle of this room. Okay? Electrons aren't the same. They can be in this region up here that's orange, and in this region down here that's blue, and pass between them without ever going through that middle region, that node. All right? This is just another part of the fantastical world of quantum mechanics. Things that are really tiny and moving really fast do not behave the same as things that are big and slow like us. All right? Calculus is great at describing big, slow stuff. You need quantum mechanics for the small, fast stuff. And this is just one of these examples where it's like super counterintuitive, but that's what the math says. Cool. So yeah, pretty cool. It's almost as if they can kind of teleport, but really it's more of a feature of how we treat them in quantum mechanics, which is as waves and not as particles. All right, cool. So now we're going to work on building our electron configurations. I sort of showed you a few. How did I get that? We're going to go to our periodic table. All right, and we're going to learn a new way to cut this thing up. We've cut it up in a few different ways before. We're going to learn a new way here, and that's going to help us figure out our electron configuration for these atoms. Yeah, there should be stuff back there. All right, the first thing we're going to do is we got to move helium. Helium's in the wrong place. All right? Helium is over there with the noble gases because it is a noble gas. It is not reactive at all because it has a full valence shell. But for purposes of assigning our electron configurations, we want helium to be over here. Position number next to our hydrogen. Position number 2. All right, so the first sort of like cut we're going to make here is for these first 2 columns on our periodic table. All right, these elements are what we call our S block. All right, remember we discussed these orbitals and we kind of talked about their natural order. What would come next after S? S, P, D, F, yep. All right, so our next block we're going to do is over on the other side of our periodic table with a bunch of our non-metals. This is what we call the P block. All right, we got this middle portion where our transition metals live. This is the D block. All right, and then the part at the bottom of our periodic table that sits kind of aside is that last one, the F block. Okay. First of all, one thing to note, our periodic table, a lot of periodic tables are formatted like this with the F block sitting below. You can see up on the wall here an example of where that F block is correctly inserted into the periodic table. So just sort of make note our elements here between lanthanum and hafnium, there's this big jump in atomic number. Right? That's because this is where that F block would be inserted. Cool, so we cut up our periodic table into these different blocks, all right? And notice how they correspond to those different shaped orbitals. Our spherical, our peanut, our daisy donut, and the F, all right? Now we're gonna learn how to divide this up into these rows here, all right? So what I mean by that is we need to number our S block. Our first row is row 1, then row 2, then row 3. It just goes in order, all right? So 1, 2, 3, 4, 5, 6, 7. These are going to correspond to those principal quantum numbers. Our S block, we start numbering at 1. Our P block, we're going to start numbering at 2. So that first row in our P block is 2, 3, 4, 5, 6, 7. All right, our S block, we started numbering at 1. Our P block, we started numbering at 2. Our D block, we're going to start numbering at 3. Okay, so this is the 3D row, 4, 5, 6. And if you were tempted to think that it would be 4D because it's the fourth one down on the periodic table, that's not how it works, all right? Just trust me on this one. It is the 3D row on our periodic table. All right, and then if our S started at 1, our P2, our D3, what do we think we're going to start numbering our F block at? 4. So that first row in the F block is the 4F row. I guess I can put it over here. And the last one is the 5F row. All right, so given that we just cut up the periodic table like this, let's go back and revisit those electron configurations that I said you were just going to trust me about. Hydrogen was 1s1, helium was 1s2, and lithium was 1s2, 2s1. Okay? Well, if we look at hydrogen on our periodic table, what we'll notice is that it is the first element in that 1s row. So that's how I knew to put 1 electron in that 1s orbital. Helium is the second element in that 1s row. So that's why I knew to put 2 electrons in its 1s orbital. All right, then we get down to, helium. Then we get down to lithium. All right, lithium is now in the first column of the 2s row. So that tells me what the last orbital in my electron configuration is. All right, an element's position on the periodic table tells you its last orbital in its electron configuration. So then how do I finish this off? It's also going to contain everything that came before it. Okay? And what comes before 2s is that whole 1s row. All right, if I look, lithium's element 3, it's going to include the orbital that came before it on the periodic table, the 1s orbital. Okay? And so it now has, since we're past it, a full 2s orbital. Cool, so then let's do boron. All right. Boron lives in which block? The P block. And it lives in which row? The 2p row. So our last orbital in boron's electron configuration is 2p. And how many electrons live in that 2p orbital? Well, which element is boron in this p block? It is element 1. So it's only got one electron in that 2p orbital. All right, but then it's got to contain everything that came before it as well. And what came before that 2p orbital? That 2s, right? So let me just get rid of some of my markings here. Okay, we can see that what comes before 2p? 2s. All right, again, look at that element number. Boron is element 5. You got to look at element 4. So now my electron configuration, whoops, is going to be 2s2. And what came before the 2s? The 1s. Cool. All right, so boron's electron configuration is 1s2, 2s2, 2p1. Again, where boron lives on the periodic table tells me the last orbital in its electron configuration. Whoops. All right, and then I got to include everything that came before those orbitals on my periodic table. All right, cool. So y'all are going to take a minute and do silicon for me. All right, so where does silicon live on our periodic table? What block? The p block. And which row is it in? The 3p row. So the last orbital in its electron configuration is 3p. All right, and then how many electrons live in that 3p orbital? 2. What comes before 3p? 3s. Right? If we look at element 13, follow that back to element 12, 3s. And how many electrons are going to be in that 3s orbital? It's going to be full. There's going to be 2. Okay, cool. So now what comes before 3s? 2p. Cool. So remember, element 11, it's not going to be the next row up. I got to look all the way on the other side of my periodic table to element 10, where neon lives, which is that 2p row. And how many electrons can I fit in those 2p orbitals total? 6. Right? Notice how there are 6 columns on our p block. What comes before 2p? 2s, 2s2, and in front of that, 1s2. Okay? So silicon's electron configuration is 1s2, 2s2, 2p6, 3s2, and then 3p2. There are 2 electrons in that last p orbital. All right, just for fun here, let's do one more. Let's do an element that lives in the p block. I want you to tell me cobalt's electron configuration. I'm sorry, the d block. Cobalt's electron configuration. Okay, we haven't numbered our D block yet. 7, 8, 9, 10. So there are 10 columns. So what are the maximum number of electrons we can have in our d orbitals? 10. Cool. Find cobalt. The last orbital in cobalt's electron configuration is going to be 3d7. Right? It's in that third row of the d block, or what we call row 3 of the d block, and it is element 7 in that third row. And then I got to include what comes before it. What comes before the 3D? 4s. So notice that it is not in numerical order here. Before 4s, 3p, 3s, 2p, 2p6, 2s2, and 1s2. Cool? All right. And it is very wonderful and nice and neat that it works out with this pattern on the periodic table here. But again, where does all this crap come from? I guess real quick, just to rewind, what the heck does this mean? 1s2, 2s2, 2p6, 3s2, right? Again, it's where the electrons in a silicon atom live. It's got 2 electrons in a little teeny tiny sphere, 2 more in a slightly bigger sphere, 2 more in an even larger sphere. And then it's got 6 of them in those peanut-shaped orbitals, with another 2 in slightly larger peanut-shaped orbitals. Okay, and again, it's very nice that it follows this pattern on the periodic table, but where did this all come from? What are we going to blame it on? All that big ugly math equation, right? This is what the math equation tells us a silicon atom looks like. Cool. All right, so wonderful. We're going to learn how to do 2 things with these electron configurations here. Okay. The first is what we're going to call electron configuration diagrams. So we're going to translate that same information into a diagram form. Cool. All right, so again, we have 2 very similar things. Our electron configurations. All right, we're going to need one of those to work with. That is what we just learned how to do based on the periodic table. So everybody take a second. We'll do a little atom here. Oxygen. Everybody take a second and tell me oxygen's electron configuration based on what we just learned. Yep, 2p4. One s2, 2s2, 2p4. And we're going to learn how to take that information and turn it into an electron configuration diagram. Right? So that same information just kind of diagrammed out in this little chart. This little chart is a super popular way to depict electrons in their orbitals. You'll just see it kind of throughout your chemistry career, specifically in like spectroscopy type of stuff, where you're exciting electrons. Very exciting. All right, so step 1 of our electron configuration diagram is to draw a y-axis and label it energy. Okay, so I'm going to draw a y-axis and I'm going to label it energy. Check, check. Okay. So now I need to orient. So notice how we're going to have this energy axis here, right? What we're going to do is order these orbitals in terms of increasing energy on my diagram here. And fortunately, when we built our electron configuration from our periodic table, we already organized them from lowest energy to highest energy. now what we're going to do is on our diagram, we're going to draw boxes. To represent our orbitals. In the order of increasing energy. Okay, so what do I mean by that? I'm going to take my diagram here with my y-axis, and I'm going to draw a box down at the bottom. Lowest energy here, my lowest energy box. All right, and this is going to represent that lowest energy orbital in my electron configuration, my 1s orbital. Okay, I'm going to draw another box that's higher in energy. This is going to represent our 2s orbital, because that was the next one in terms of our increasing order from our electron configuration. All right, and then I get to the next one, and I need to draw my 2p orbital. But remember, how many p orbitals were there? 3. So I'm not going to draw just one box. I'm going to draw 3. All right, and that represents my 2p orbitals. All right, so let's just make a note. We're going to draw our boxes to represent increasing orbitals. When we draw those s orbitals, we got just one box. We got the p orbitals. Those were 3 boxes. What about the d orbitals? 5. And the f orbitals, 7. All right, because each box represents an orbital, and as we said, in that D, there are going to be 5 different orbitals, those different shapes. Well, they're the same shape, but oriented differently in space, minus that one weird donut one. Okay, now last step is we need to fill in this diagram with electrons. And we got certain filling rules for our diagrams. All right? We need to fill from lowest energy to highest energy. So which orbital am I going to start with? 1s, my lowest energy orbital here. How many electrons are going to go in that 1s orbital? 2, because according to my electron configuration, there are 2 in there. Okay? So we're going to start by putting those electrons into that lowest energy orbital. Importantly, you can have 2 electrons per orbital. So when I go to draw my electrons in here, I'm going to draw them as arrows. And I can fit 2 of them into this box here. But importantly, one has to be what's called spin up, and the other spin down. We represent the spin up arrow with a upward pointing arrow, and the spin down, electron with the downward pointing arrow. So if I fill in my other electron, because I'm allowed to have 2 per orbital, I would fill one spin up, arrow pointed up, and the other one spin down, arrow pointed down. Okay, so now I've filled that 1s orbital. I'm going to move on to the next one here, the 2s orbital. How many electrons am I going to put in there? 2. So again, one of them will be spin up, one of them will be spin down. All right, and then our last filling rule here is when we get to orbitals that are equal energy. All right, notice how on my y-axis, all p orbitals here are at the same energy level. For equal energy orbitals. we have to half fill first. Then go back and double up. All right, so what the heck do I mean by that? How many electrons am I going to put in that 2p orbital according to my configuration here? 4, right? So I need 4 arrows in these boxes here. How many am I allowed to put per box? 2. One has to be spin up, one has to be spin down. But now my last filling rule, everybody look up here real quick. I'm going to fill in these 4 electrons by half filling each one of these boxes first, and then I'll go back and double up. Okay? So you go through, that's our last rule, is for equal energy orbitals. You half fill first, then you can go back and double up. And this is my electron configuration diagram for an oxygen atom. It conveys the same sort of information from that electron configuration that we wrote out based on the periodic table, but just kind of in this diagram form. And again, this is useful for describing certain experiments, so you'll see this sort of thing a lot in your chemistry career. Cool. All right. I want you to build one real quick for silicon. We already got silicon's electron configuration. Okay. That was what we had done previously based on our periodic table. All right, I want you to take a minute and draw a diagram for the electron configuration of silicon. All right, so how many electrons should be in that 1s orbital in my diagram? 2. In fact, all of these boxes are going to be full until I get to the very top here, okay? But I'm going to be good, and I'm going to follow my filling rules for this 2p orbital, where you half fill first, and then go back and double up. Okay, boom, boom. That'll be really important for here because in my final orbital there are only 2 electrons, so when I go through and follow my filling rule and half fill first, I'm left with this as my electron configuration diagram, right? To be clear, if you had put both of those electrons in that first box, that would be wrong. You instead have 2 spin up electrons, 1 in each p orbital, okay? This sort of spin up, spin down business is not something that's very intuitive as well. It is another thing that kind of comes out of quantum mechanics. By spin, the best way to kind of have a mental picture of is to imagine that these electrons are spinning around like tops as they're traveling through space, all right? They have some angular momentum associated with them, okay? And it turns out that in the world of electrons, some are spinning in one direction and others are spinning in the other direction. And the only way that they can live together, that they can occupy an orbital, is if they have opposite spins, right? If one is spin up and one is spin down, okay? It is one of those weird aspects of quantum mechanics that has then since been proven, and it's just the truth that it turns out that a lot of particles have spin associated with them.
Does that half-filling rule only apply to the p orbital?
No, any equal energy orbital. So if we got to a d orbital, there would be 5 boxes in a row, and you would go through and only half fill them. Cool. All right. So the next thing that we're going to do is just to kind of make our lives a little bit easier. And that is we're going to learn an abbreviation for our electron configurations, what's called the noble gas abbreviation. Okay. So first, you're going to, so that we have some examples to work with here, you're going to give me the electron configuration of chlorine and neon based on where they live on the periodic table. Okay, not the full diagram, just the 1s1 or 1s2, 2s2 business. All right, for each one of these elements. All right, let's do this first example full out here. Bring up our marked up periodic table. We're going to find our chlorine atom. According to where chlorine lives on the periodic table, the last orbital in its electron configuration is 3p, and there are 5 electrons in that 3p orbital. Then I got to include everything that comes before that, which is 3s, then 2p, then the 2s, followed by the 1s, and all of those are maximally filled. Okay, so here's my electron configuration for chlorine. Again, based on where chlorine lives on the periodic table, I know it's in that 3p orbital, the last one in its electron configuration, and there are 5 electrons there. Everything else is just including what comes before it. Cool, all right. So for chlorine, we said 3p5. Okay, cool. And then for neon, if we did the same thing, it would be 1s2, 2s2, 2p6, right? It's got a full 2p orbital based on where neon lives on the periodic table. Okay, now, if you will notice, neon's electron configuration exactly matches these first 3 orbitals in chlorine's electron configuration. So we can summarize chlorine's electron configuration with what we call the noble gas abbreviation, where we say, all right, chlorine's electron configuration is whatever neon's is, plus that extra bit at the end there, the 3s2, 3p5. Okay? And this sort of bracket Ne that I put at the beginning means insert neon's electron configuration in order to finish off chlorines. All right, so this is just kind of a shorthand that we can use to make our lives easier. Why don't you all take a second and use the noble gas abbreviation to tell me what selenium's electron configuration is. All right, so what noble gas am I going to use for selenium's electron configuration? Argon. Okay, so in parentheses Ar. Why can't I use krypton? Krypton is so close to selenium. Because it's in front. Because it's got more electrons than selenium does. I can't summarize what selenium's got by using an element that has more electrons. So I got to use the next smallest noble gas, argon. All right? But then I have to include, argon takes me all the way up to 3p in this electron configuration, but I got a bunch more that's going to come after that I'm going to have to include here. All right? I'm going to have to include those two 4s electrons, then those 3d10 electrons, and then finally I get to my 4p, and there are 4 electrons. All right, so my electron configuration for selenium using that noble gas abbreviation, I use argon plus everything that comes after argon but before selenium, right? So I also have to include the 4s, the 3d, and my 4p where selenium lives. Cool? All right, wonderful. Obviously, the further down the periodic table you go, the more and more orbitals it has, so the more and more handy this thing comes in, so this thing comes in more and more handy, right? Doing Bismuth's electron configuration, the full one, would be pretty tough. Cool. All right, so last thing that we're going to kind of discuss, really go back and revisit, we've talked a lot about are ions. All right, and specifically trying to look at those electron configurations. Okay, let's go back to what we already did here when we were talking about these electron configuration diagrams. We built that electron configuration diagram for that oxygen atom. All right, so let's go back and kind of revisit that. I'm just going to copy. All right. Okay, oxygen was 1s2, 2s2, 2p4, and then we went as far as to actually build that electron configuration diagram. We had our boxes. Cool. 1s, 2s, 2p. All right. So now, though, we're trying to think about ions here. And really what we're trying to get at is the oxide ions electron configuration. Okay? Well, look at this diagram here. Let's look at this diagram. In order for oxygen to become the oxide ion, let's think about our charge balancing here. What's going to happen to that oxygen atom? It's going to have to gain 2 electrons. Okay? So now let's look at our diagram here. If we wanted to instead do the electron configuration diagram, not for oxygen but for oxide, I'm going to need to add 2 electrons to this diagram here. I'm going to make them a different color just to make a point. Where do we think we're going to put those 2 electrons in this diagram? In the last 2 spots, right? There are exactly 2 spots open on this diagram. 1 spin down arrow in the middle, 2p, 1 spin down arrow in the last 2p box. Right? So why does oxygen accept 2 electrons? Because that's what it's got room for. It's got these 2 half-filled p orbitals that can accept those 2 electrons, becoming that oxide ion. Okay? Cool. So if we were going to then translate, everybody take a second and translate this into an electron configuration. This is the diagram form. What would that be if you wrote it all out in a line just like we did for the oxygen atom? Okay? How many electrons would I put in that 2p orbital? 6. It's going to be completely filled. Which would be the same as what element if I was using my noble gas abbreviation? Neon. Right? The last element in that 2p row. So we kind of mentioned this at the beginning when we said that why oxide likes to accept 2 electrons. It wants to be like the noble gases, we said, right? So what exactly does that mean in our little refined picture of what an atom is in terms of these orbitals? It means it's going to accept those 2 electrons into that empty space to adopt the same electron configuration of those noble gases, of that noble gas neon. Okay? So elements will always form ions in order to adopt the noble gas configuration, or rather the electron configuration of noble gases. All right? And the real like from an energetic standpoint, the benefit are all these completely filled orbitals. We got no empty boxes here, all filled orbitals. That is nice and super duper stable in the world of orbitals and all that crap, in the world of quantum mechanics. Okay? Cool. So then lastly here, let's just do the electron configuration for sodium. And then we're going to do the sodium ion. right, so if I do my electron configuration for sodium, 1s2, 2s2, 2p6, and then 3s1, when sodium becomes the sodium ion, it's not going to gain an electron, but rather it needs to lose an electron. Again, think of our charge balancing. So in looking at my electron configuration, where am I going to scratch that electron from here? I got to get rid of one of these electrons. That 3s, right? That top box, leaving me with 1s2, 2s2, 2p6, which is again neon's electron configuration, right? They lose these ions to adopt the electron configurations, lose these electrons to adopt the electron configuration of these noble gases. They're just nice and super stable, completely filled diagram here. That's just a nice, super stable electron configuration, which is why they adopt them. Cool. All right, break. We are going to kind of pick up with this next time. We're going to actually look at these diagrams again next time and learn how to say something about where each one of these electrons lives. All right, so we're going to continue this discussion next time.